nth partial sum of the sequence below, 1, 3, 5, 7, 9, then prove that your formula always works. The first few partial sums of the sequence are below. So our first partial sum would be just adding 1 together, so that's 1. Our next partial sum would be adding just 3 together, so that's, 3 onto what we had before, so that'd be 1 plus 3. The next thing would be 5, so 1 plus 3 plus 5. Next thing would be 1 plus 3 plus 5 plus 7. Next thing would be 9. Let's write that out as well. So 1 plus 3 plus 5 plus 7 plus 9. If we were to keep going with this pattern, what would be next? Well, that'd be 11 next, right? We're adding by 2 each time. So 1 plus 3 plus 5 plus 7 plus 9 plus 11. Let's see if we can figure out what the pattern going on here is. So 1 on its own, well, that's just 1. 1 plus 3, hey, that's 4. 1 plus 3 plus 5, well, that's 9. Add on another 7, 7 plus 9, that's 16. Add on another 9, that's 25. Add on another 11, that's 36. Hey, we've got an idea on what the formula is. It looks like the nth partial sum, so it looks like the nth partial sum is going to be equal to n squared. Great. So what we've got here is 1 plus 2, sorry, not 1 plus 2, but 1 plus 3. 1 plus 3 plus 5 plus blah, 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 plus something. What do we end on is equal to n squared. So we need to figure out what do we end on. How do we call out each member of this sequence? Well, we can remember what we did in arithmetic sequences. We see we've got 1 as our starting place. We add up by 2 each time. So we could realize that the nth term here, an, is equal to 2n minus 1. We verify this, right? N at 1 gets us 1. N at 2 would get us 3. N at 3 would get us 5. So this works out. So we see that what we're going up to is 2n minus 1. So our statement, the Pn statement, is that 1 plus 3 plus 5 working up until 2n minus 1 is equal to n squared for any n. So that's what we figured out our formula is for how we're adding up these, how we're getting these partial sums. As we add up more and more terms of the sequence, we've now figured out how formula, right? We figure out how does this pattern of adding things up, how does that come to be? We see, oh, we've got n squared coming up out of, we do this each time. On the first term, right, n equals 1, we've got 1, n equals 2, we've got 4, n equals 3. So we see that each time it's just squaring that number. We also have to figure out what does the sequence of the things look like, because we have to be able to figure out what do we end on. We have to be able to say what's the last thing so that we can actually work with having a left side and a right side to our statements equation. But at this point, we're now ready to prove this. All right, so now it's just up to us to prove that this is indeed true, that Pn that our statement Pn is true for any value of n, that 1 plus 3 plus 5 up until plus 2n minus 1 is equal to n squared, no matter what n we put in, as long as n is a positive integer. So first thing we prove, always prove the base case first, because it's almost always easier. Also helps you understand how the thing comes together. So base case, so P1, showing that P1 is true is going to be the same thing as showing that 1 added up until, well, we just added up to 1, right? So that's just 1 on the left side. Is that equal to 1 squared? Yep, 1 is equal to 1. That was pretty easy, right? So there's our base case knocked out. Next up, we do the inductive step. Now we want to show that the inductive step is going to wind up being true. So first thing we always do, we assume our hypothesis first. What is our hypothesis going to be? Our hypothesis will be that pk is true. What is the statement pk? Well, that would be 1 plus 3 plus up until we get to plus, plug in k for n, 2k minus 1 equals k squared. So we're assuming that 1 plus 3 plus blah, 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 plus 2k minus 1 is equal to k squared. Okay, so with that assumption that this thing is true, we need now to show that k plus 1 is going to be true as well. So now we want to show that k plus 1 is true. So showing k plus 1 is true is going to be equivalent to showing that 1 plus 3 plus dot, 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 plus 2k minus 1, sorry, not 2k minus 1, we're going to swap out k plus 1 for n here, so 2 times k plus 1 minus 1 equals k plus 1, swapping out that n as well, that n here as well for k plus 1 squared. Now remember, we want to have our hypothesis show up somewhere. We have to get our hypothesis to show up somewhere. So we realize, oh, hey, that's really this part up to here. So we can rewrite this as 1 plus 3 plus dot, dot, dot until we get to 1, that back a step of 2. So that would be 2k minus 1 forward a step by 2, we see that that would be 2k plus 1. If we work out this value here, we wind up seeing that's the same thing here, right? 2k plus 2 minus 1 is just 2k plus 1, and we want to show that that is equal to k plus 1 squared. Okay, so we bring this up here, and on the way, we're going to go, hey, right here, from here to here, we assumed up here that this was true. So that means what we've got previously, what we've got in the thing we're trying to show, pk plus 1, that part of it, is going to just be equal to k squared right here. So we can swap out k squared here. So now we've got k squared plus what still remains, so that's 2k plus 1. Oh, and we want to show that this is true, so it's a question mark here. We don't know for sure that it's true yet. It's up to us to show that it winds up being true. So plus what remained there, 2k plus 1, is that equal to k plus 1 squared? So k plus 1 squared, well, let's just simplify it. We've got k squared. We expand this. Well, k squared plus quantity 2k plus 1, well, that's just 2k plus 1. Is that equal to, what do we get when we expand k plus 1 squared? Well, that's k squared plus 2k plus 1. Hey! We wind up seeing that is indeed true. That is always going to wind up being true, so we have shown our inductive step is true. With this hypothesis in mind, we know that the next thing down the line, with pk being true, we know that pk plus 1 must be true. So because we know our base case is true, p1 is true, and we know that if something is true, then the next thing has to be true. Then since p1 is true, the next thing must be true. p2 is true, p3 is true, p4 is true, p5 is true, p6 is true, and the fireworks keep going forever and ever. We see that everything is always true. So we have that this statement winds up being true for absolutely every single n that we would plug into it. We have completed the proof. Our proof is done. Pretty cool. The only really challenging part there, right, that wasn't that difficult to proof by induction compared to the ones that we did previously. The challenging part there was being able to figure out what that formula is in the first place. So once again, if you have difficulty with that, I recommend check out the arithmetic sequences and series. There's that section, tips on finding patterns, that will really help you see how to find patterns. There's a lot of good stuff in there. All right, we'll see you at Educator.com later.